Hello friends, now in this class maybe of half an hour duration, we will take up another very important aspect of food. As I indicated in the earlier class also, that water is a very important component of the food. So now let us study the role of water in food and its influence on shelf life of the food materials. Water, you all know, is an important component of life next to oxygen. A person can live for a few weeks without food, but it becomes very difficult to live a few days without water. Water is an integral part of all the animal and vegetable tissues. It is the medium through which different cellular reactions takes place. Water helps in almost all body processes like digestion, circulation, excretion, etc. It helps in maintaining the electrolyte balance of the body and plays a role, rather a very important role in maintenance of the body temperature. Water is not only a solvent, but it also participates or take part in the several reactions either as a product or as a participant, as the case may be. And it is needless to say that water is one of the widely distributed compound in the world, and it is available or it is found in all three states of matter, that is liquid, solid and gas or vapor. It is one of the most important chemical present in food and drinks. In fact, that is sometimes that is food is said that it is a mixture of chemicals in water or biochemicals in water. And food contain wide ranging of water in it. There are certain foods which contain as low as maybe 1% or 2% like crackers, etc. On the other hand, also there are certain food which contain as high water as 96% or 98% like fruits or vegetable like cucumber, tomato, etc. So, in fact, it depends, that is in general fruits and vegetable contain more than 90% water. Milk, mammalian milk contains around 88 to 90% or some 86% water. Flesh or meat 60 to 75%. Dried foods like such as figs, raisins, etc. they may contain 18 to 20% water. Means that is there are wide food material, they contain wide ranging amounts of water, and this water influences in fact all the characteristics like appearance, texture, flavor, other characteristics of the food. In fact, you can see that milk which has 88% approximately water is a liquid food. On the other hand, vegetable like tomato which has which contains around 96% water, cucumber 98% water, but they are solid food. So, it is not only the water content, but the manner in which water is present into the food material that gives its desired characteristics, that is physical characteristics, chemical characteristics and so on. In fact, water is involved in most of the changes that take place when the food is cooked or when the food is processed. In fact, food spoilage also is related to the water content. Milk, again you take the example of milk, you take the example of a fruit or vegetable, you take the example of a grain. It is the water content and the form in which water is present, we will see little later towards the end of this lecture, that is how water is available for the various chemical processes, for the various microbiological processes, etc., that influence it. So, it is important in bringing about desirable changes into the food material, or at the same time water is also responsible for the spoilage of the food products. Okay. Even some of the desirable or undesirable changes that take place in the water, okay, or take place, desirable and undesirable changes that take place when the food is cooked, are due to the property of water as a solvent. You can take example of color development or flavor development in coffee brew and tea brew. That is characteristic flavor or characteristic color of the coffee or tea is because of the solubility of water. When we put coffee or tea in water, then various flavoring compounds or various coloring compound get solubilized in water, and then we get the tea beverage or coffee beverage. Even there are many water soluble vitamins, okay, and depending upon the type of the cooking processes or washing processes, even these water soluble vitamins, they may be leached out, and that again here the solubility of water is major criteria for this. Water is also a dispersion medium in food, and as I indicated that too much water in foods can be a danger, as it favors the growth of undesirable bacteria and other microorganisms. And in fact, the aim of modern food technology is to keep the water content of many foods as low as possible, so that to get the maximum shelf life. Now, let us go study little details of the properties and characteristics of the water. The physical constants of water, like water is H2O, we will see in the other slides also in this class itself. So, H2O, and if you compare this with the other molecules of similar atomic composition or similar molecular weight like H2S, HAF, ammonia, etc., then we find that water has unusually different or sometimes higher values for the physical constants such as melting point, boiling point, surface tension, specific heat, dielectric constants, etc. Even the heat of fusion, vaporization, sublimation values for water are also high. Another unusual property of water is that it has maximum density at 4 degrees Celsius and not at 0 degree Celsius, which is the freezing point of the water. Otherwise, in other materials, other fluids, normally they are maximally dense at their freezing point, but it is not true in the case of water. Even water and ice, the two forms of the water, that is the liquid form and solid form of the water, if you see their characteristics, it varies. Thermal conductivity of ice at 0 degree Celsius is approximately 4 times than that of water at the same temperature. And what does it indicate? It says it indicates that ice conducts heat at a much faster rate than immobilized water. And this is seen also in the case of processes like freezing and thawing. We can conduct the freezing very quickly, but the thawing you cannot conduct it so quickly like freezing. Why? If during the freezing, with the progress of time, there is ice phase enlarges. So, the heat transfer medium becomes the freezing. So, freezing process can be conducted at a very quickly, but in thawing it is just a reverse of that. During thawing, with the progress of the time, heat transfer medium becomes water. So, it the conducts, that is water conducts heat energy at a lower rate. So, thawing is normally a slow process in comparison to the freezing. So, here let us see the structure of water molecule, which I have shown in this figure. You can see water is formed here, two hydrogen atoms are combined with one oxygen atom. Okay. The properties of the water, which we have seen in the earlier slide, unusual properties, in fact, they are closely related to its structure. They can to a great extent be explained by the structure of water. And those unusual properties of water suggest that there is existence of strong attractive forces among the water molecule. The observed differences between the properties of water and ice also indicate that even the structure of water and ice are not same, they are not common, and that is why, like the thermal conductivity you have seen, water and ice, they have different thermal conductivity properties. So, it means that it further says that even the structure of water and ice is not same, there are differences. So, means that is the strong attractive forces etc. are there. That is water molecule, if you see, they have some hydrogen bond present in that, both, that is the, as I told you, that is the water molecule, that is oxygen and two hydrogen atoms are connected by covalent bond, okay, and the bond angle is 104.5 degree. Okay. The water molecule, although it is considered to be electrically neutral molecule, but there is an imbalance of the charge, that is mainly because of the arrangement of atoms. You can see here in oxygen, both the hydrogen atoms, they are placed on the same side of the oxygen atom. So, the side where hydrogen atoms are located, that side is slightly more positive, whereas the other side is slightly more electronegative. Means that is in the same water molecule in the oxygen atom, both positive and negative charges are, there is an imbalance of the electrical charge, and this imbalance of the electrical charge in fact attracts, that is one water molecule attracts the other water molecule, which you can see here, that is oxygen of the one water molecule attracts the hydrogen of the other, that is they get attracted with the help of hydrogen bond. Okay. Here hydrogen of this water molecule get attracted with the oxygen of the other water molecule, and so it is this hydrogen bonding means that is water actually there are multiple hydrogen bondings, right, and this type of multiple hydrogen bonding on a 3-dimensional basis actually that gives the logical explanation for the characteristics of the water. And you can see here in this structure, that is one water molecule can hydrogen bond with 4 other water molecules at a time, and the higher values of the physical constant are basically the energy required to break these hydrogen bonds, right, and this provides a logical explanation. Okay. Water, in that it is one water molecule combined with hydrogen bond with the 4 other water molecule, but you just imagine that is where are like there is a bucket of water, that is in the pond, there is a pool of water. So, what is this hydrogen bonded arrangement of the water? What are the theory? The two theories are explained in this connection. One is the homogeneous model, another is the mixture model. The homogeneous model explains that intermolecular hydrogen bonds are uniformly distributed throughout the water molecule. That is, whatever throughout the total amount, that is intermolecular hydrogen bonds are uniformly distributed, and so that each water molecule has essentially the same environment. On the opposite, in contrary to this, mixture model explains that no, they are not uniformly distributed, rather at any given moment the intermolecular hydrogen bonds are concentrated in localized multimolecular clumps or clusters of water molecule. In fact, the most widely accepted model appears to be the mixture model, because this explains the characteristics or reactions etc., which is seen normally in the processes. So, the mixture model appears to be the more valid model, and therefore, it is more widely accepted model. Now, let us see the structure of ice. You have seen that the properties of ice and water are different. So, obviously, there is some structural difference in water and ice. You have seen in the earlier hydrogen bonded structure of water that it is a open structure, but here you see this is the structure of the ice. It is a closed structure. Structure of water, hydrogen bonded structure, it is open structure. Okay. So, when water is frozen, right, then this a regular hexagonal pattern of hydrogen bonded structure results, and this closed structure is formed. That is, open structure is changed into closed structure, okay, and this structure, closed structure, actually accounts for the properties of the water, and this difference you can see here in that structure of ice. There are ample amount of empty space, and therefore, this is that is the, if you take same amount of water and same amount of ice, and because of this empty space available in the ice structure, it is less dense, it is lower in weight, and that is it. Water, in fact, ice, it is usually less dense. Water, because of the more empty space in it, and therefore, it floats, the ice floats in the water, and this is in fact you can say natural defense mechanism has been provided particularly by the nature, particularly to the aquatic lives. Otherwise, you could visualize what would be the situation if the solid water like ice is not floating on the water, that is during in the seas, in the rivers etc., during the winter season when the temperature goes below in the low temperature regions. There the aquatic lives, they go underneath, they usually they comfortably rather live in the warm water below the blanket of the ice on the surface. So, this properties, this structure difference in the water and ice explains the properties difference in the water and ice as well. Okay. Now, let us see, that is a little bit what are the solutes of the effect of solutes on water structure or water characteristic, that is how some sorts of solutes are put into the water, then how the normal hydrogen bonded structures of water is influenced, whether how it is disturbed or it is further encouraged, right. And water is called an universal solvent, and there is a considerable justification for this, because the substances that are themselves polar or ionic are readily soluble in water. So, like sodium chloride or such other component, when it is put into the water, what happens, how it dissolves. Okay. So, there are different types of solutes, that is maybe one type of the solute is which can get dissociated, like sodium chloride, if you put into the water, then it may be get dissociated into sodium ion and chloride ion. There might be other type of solute like inert solute or the solute which can form hydrogen bond. So, different types of solutes, when they come in association with water, they influence the characteristics or water differently. So, normal is hydrogen bonded structure of pure water is disrupted by the association of dissociable solutes. Okay. Some ion in dilute solution break the hydrogen bonds of pure water, whereas the other have a net structure forming effect. Ions which are normally smaller and are multivalent, mostly positive ions like lithium, sodium, potassium, lithium, sodium, hydronium, calcium, etc., are net structure formers. On the other hand, the large and monovalent ions, mostly negatively charged ions, and large positive ions such as potassium, rubidium, ammonium, chloride, bromide, iodide are the net structure breakers. And in a concentrated salt solution, the structure which is common in the vicinity of ions is likely to predominate. Solutes capable of forming hydrogen bonds such as urea may be expected to enhance or at least not disturb the normal structure of water. However, it may so happen that distribution and orientation of the solutes hydrogen binding sites may be geometrically incompatible with the normal hydrogen bonded structure of water, and this may cause disruption of some of the hydrogen bonds of water, like water hydrogen bonds. However, total number of hydrogen bond per mole of the solution will not be substantially changed, because the solute here has the capacity to form hydrogen bond. So, when it is introduced into the water, then the water hydrogen bonds might be replaced with the water solute hydrogen bonds. The total number of hydrogen bonds will be, and this newly formed water solute hydrogen bonds are of particular importance when macromolecules are involved. And you can see, if in a macromolecule there is water hydrogen bonding sites, if they are uniformly distributed throughout the solute molecule, then it is conceivable that a structure zone of water exists at the macromolecule water interface, and a considerable number of carbohydrate, proteins, steroids, hormones, etc., appear to have hydrogen bonding sites. Solutes which are inert in nature, such as hydrocarbons and the non-polar groups of compounds like fatty acids, amino acids, protein, etc., have the structure forming action when introduced into the water, and solute of this nature situate themselves at the boundary of the bulky hydrogen bonded cluster of water molecule, and thereby encourage the formation of more extensive water hydrogen bond, and this causes the solute to become partly or wholly surrounded by more than normal amount of structure. In most proteins, about 40% of the total amino acids have non-polar side chains, and these non-polar groups have a structure forming action on the adjacent water, and the interaction between the water and non-polar groups has an important influence on the reactivity of the proteins as well as on their native tertiary conformations. So, after having this discussion about the properties and structure of water and ice and their differences, let us see how these waters are present into the biological material. In fact, that is gives the concept of bound water. Okay. That is the food and living systems contain bound water molecules due to their biological structure or the presence of solutes, and the intensity of binding obviously varies, but only those molecules of water that are mobile, mind it, that are mobile and bound least formally determine the observed water activity. In fact, bound water behaves differently from that of the pure water. And remember, in the earlier class I told you that it is not the total water present, rather it is the type of water or the water present in which form that determines its availability for the chemical and microbiological processes. So, depending on the extent of boundedness, water is grouped into 4 types like type 4, type 3, type 2 and type 1 bound water. Of course, distinct boundary might not be there, but in all the 4 types of water, but for just some sort of understanding, this classification is provided. There are of course intermediate stages of boundaries as well. Type 4 bound water is the one which has full activity and it does not exist except in the free state. It is the other type, the type 3, type 2 and type 1 bound water which are found in the biological matter. Type 3 bound water is the one which is present physically entrapped in tissue matrix as well as in solutions, and this type of water represents the majority water in plant and animal tissues. The activity of this type of water is only slightly reduced than the normal water, and this type of water is actually available for the growth of microorganism, enzyme activity, both hydrolytic and oxidative as well as non-enzymatic browning. And the water content of the food can be brought to about 15 to 20% if there is type 3 bound water is removed, of course depending upon the type of the food. And if this type 3 bound water is removed, means there is the growth of the microorganism, enzymatic activity, non-enzymatic brownings, all these reactions will be eliminated. Type 2 bound water is more firmly bound than the type 3. Its activity is further reduced substantially. It permits only enzymatic activity, that too only hydrolytic enzymatic activity and non-enzymatic browning. Removal of this type of water eliminates the possibility of microbial growth and greatly reduces the most of the chemical reaction processes. And this type of water, if it is removed, water content of the food of course may come to the range of maybe about 5 to 7% or so, depending upon the type of the food. Type 1 bound water, on the other hand, say that it is the water which is more firmly bound, okay, than type 2, and the water activity of this is further reduced. Even only partial removal of this type of water can be accomplished by the conventional dehydration processes. The degree of binding in this case is such that any reaction depending upon the solution is so slow that it becomes very difficult to measure. At this stage, of course, there is an acceleration of the lipid phase reaction, which we will see in the next slides. So, by this concept of water, bound water and free water, it becomes clear that it is the water activity which actually is important, it plays an important role. So, what is water activity? It is expressed as P by P0, where P is the partial pressure of water above the food sample, and P0 is the vapor pressure of pure water at the same temperature. So, the ratio of partial pressure of water above the sample to the ratio of the vapor pressure of pure water at the same temperature is defined as water activity. Water activity can also be defined as equilibrium relative humidity expressed in decimals. But mind it here, there is water activity is the intrinsic property of the food sample, whereas equilibrium relative humidity is a property of the atmosphere in equilibrium with the food. So, to find out the water activity in terms of equilibrium relative humidity, one should conduct the experiment, and which becomes generally time consuming and tedious process, because even a smaller sample of 1 gram size or so, it takes very long time to equilibrate the humidity of the food with that of environment, that is to get, and in larger sample almost it becomes completely impossible. So, now we have a good instrumentation facilities by which this water activity and other things can be measured. So, the important thing is here that it is the water activity of the food which should be taken into consideration. Now, let us devote few minutes time to another important aspects of the water, that the water activity versus food stability. How the changes in the water activity influences the stability or storage life of the food material, and this I have shown here in the form of this slides, which is of course has taken from the standard book of food chemistry. Here that is the reaction rate, that is the rates of the microbial growth processes, enzymatic reactions, oxidation reactions figure C, and Maillard reaction like lysine loss or brown color development, or other reactions, important reaction like chlorophyll loss and vitamin B1 loss etc. in the food, as well as the Jacobson isotherms. This changes in the moisture content, gram water per gram dry matter, how it changes with the change in the water activity, which we call Jacobson isotherm. And you could see here in the figure C, where the lipids in potato chips, there is the oxidation reaction in the lipid, it deserves comment. If you could see that, have a comparison, look at the figure C and figure A of Jacobson isotherm, and you find that the lipid oxidation reaction is running, or it is taking place at a comparatively faster rate when water activity is very low. Then when water activity increases or addition of water, when it comes to the boundary layer of zone 1 and zone 2, this lipid oxidation comes to the minimum. Further addition, further increase in the water activity results into the increase in the reaction rate of oxidation, lipid oxidation, and when it comes to the boundary zone of zone 3 and zone 2, that is maybe to the intermediate moisture level range, this again becomes maxima, and although it is not shown in the figure, further increase in the water results into the decrease of the lipid oxidation reaction. It may follow that this thing. So, what are the explanation provided for this? That the water added in the earlier region in the lipid oxidation reaction may accelerate the oxidation by increasing the solubility here in this reaction. That is, when there is very less water activity, it is high, it is decreasing, and in this region it is decreasing, because it is said that in this first and second zone of this, there is a dilution of the maybe that is the factors which are causing of the that is the catalyst etc., and which results into the their reduces their effectiveness and which decreases the rate of reaction. In the boundary zone, that is the of 2 water zone, here this increase, that is increase in the water content in this, it says that it accelerates the oxidation by increasing the solubility of oxygen, that is more oxygen becomes soluble to the, and because of this even the macromolecules swell and this exposes more catalytic sites for the more reactions rate, and the reaction rate decreases. Further increase in the water, and here excessive dilution of the more than 0.8 added water may retard the rate of a suggested explanation is that there is a dilution of the catalyst, and since catalyst is diluted, it reduces its effectiveness and rate of the reaction is. In other figures, you see figure A, figure D and figure E, which are basically microbial growth, Maillard reaction and other miscellaneous reaction like chlorophyll loss and vitamin B1 loss. You can say most of these reactions, they have maximum activity towards the intermediate zone level, intermediate AW level, 0.75 to 0.85, right. And what is the explanation provided for this? That for those reactions in which water is a product, an increase in the water content can result in product inhibition, whereas in those processes or reactions where water content of the sample is such that solubility, accessibility and mobility of the rate enhancing constituents are no longer rate limiting, the further addition of water will dilute the rate enhancing constituent and decrease the reaction rate. For the chemical reaction in all, you can say A, B, C, D, E, F, in almost all these processes, if you compare with that Jacobson isotherm figure F, we see in majority of this that is they have the typically minimum reaction rate towards the first zone, that is the interface of the zone 1 and zone 2 of the isotherm. Okay. So, the means that is at this water activity, at this water content, the reactions are typically they are occurring at a very low rate. So, this water content of the food corresponding to this first encountered minimum desorption is called as monolayer moisture content, and this monolayer moisture content or monolayer water content provides a good estimate of the water content, providing the maximum stability of dried product. Means that is, if you want to dehydrate a product, if you want to dry a product and you want that this dried product should have maximum stability. So, you must dry it to its monolayer moisture content, and of course, you must take care by appropriate means of packaging and other methods during storage and handling that it should not reabsorb moisture, it should maintain its water content to its monolayer value, so that the almost most of the chemical reactions, microbiological reactions and other reactions are done. So, in this equation like AW divided by M1 minus AW is equal to 1 by M1C plus C minus 1 M1C AW. This equation can be used to compute the monolayer moisture content. One can conduct the experiment, one can find out EW at various conditions etc., and then fit the equation in this form like you can see a plot between AW by M 1 minus AW versus AW, which is known as BET plot. It should yield a straight line. So, from this figure one can found in this figure M1 is the monolayer moisture content, M is the initial moisture content gram water per gram dry matter of the food, and of course, C is a constant, AW is the water activity. So, one can conduct the experiment before drying, depending upon this monolayer moisture content may vary, it may be 0.3, it may be 2, it may be 1.5 or other thing depending upon the food material etc. Water content may vary, water activity may vary. So, one should find out experimentally that value, and then dehydration should be, food should be dehydrated to that level of water content. So, this is one aspect, but in addition to this lower, that is lowering the water activity, obviously it reduces the chemical reactions, it reduces the microbiological, but at the same time it also influences the quality. Otherwise, food technology was very simple, you just follow dehydration practice and you remove its moisture content, but removing this moisture content also influences the textural characteristics, sensory characteristics, right. It is a reconstitution. A fruit, you dehydrate it into a fruit slice, all right. Then this fruit slice, it should be edible. When you rehydrate it before eating, it should get at least again good water and good textural characteristics to reabsorb water proper manner, right. Even suitably lower water activity are required, maybe 1% or 2%, sometime less than that. If the crispiness of crackers, crispiness of the popcorn, potato chips etc. is to be retained, if during storage, if this water content increases, their crispiness is lost. You do not get that crunchy texture, you do not get that feeling. On the other hand, if that granulated sugar, you want that it should remain free flowing, it should not cake, it should not form lump during storage. Even milk, dry milk, instant coffee etc., if they should remain free flowing, which is in fact in the instant coffee, it is very highly hygroscopic. If it just comes in the contact with the environment, it absorbs water and it forms lumps, it forms cake, even stickiness of the hard candy. So, if all these are to be prevented, water activity and water content must be maintained to the desired level, and the maximum water activity that can be tolerated in dry materials without incurring loss of desirable properties are normally in the range of maybe 0.35 to 0.5 water activity, of course, depending upon the type of the product, its constituents etc. Suitably high water activity are needed in soft texture foods or even high moisture intermediate food, intermediate water activity foods or even intermediate moisture food. In that, to avoid undesirable hardness etc., this water activity should be. So, friends, water activity becomes a very important criteria. So, one must see there are two aspects that one should use a suitable or appropriate methods for controlling the water activity, for removing the water activity, for bringing the water activity to the desired level which gives maximum stability. But while doing so, one should say that yes, water activity has come to the desired level, but it should not influence the eating qualities, it should not influence the organoleptic or sensory qualities of the food, otherwise whole purpose will be defeated. With this, I thank you for your kind attention.